Well, ladies and gentlemen, welcome back. This is going to be Friday, March 27th. You guys have all had a wonderful past couple of days. Being your economics teacher, once again, I would encourage you to get off social media and rather go and take a look at the stock page. There's a lot of opportunities for buying going on right now, especially with a potential fiscal stimulus plan coming. But you're going to have to take an economics class to be able to figure that out. So here we go again, rotation of axes. And I remind you, everything that we do, if you feel you already have grasped it because you've read the lesson in the textbook, I am just paralleling the textbook itself, and or you feel very confident about what you're doing, do not feel obligated to watch every one of these videos at any point. That's entirely up for you to decide. Nonetheless, our goal today, we're going to review graphing a conic with b is equal to 0. You should have done that both in Algebra 2, potentially, college algebra, definitely, and even college trigonometry. So hopefully you're pro. Second of all, we're going to review graphing from college algebra specifically, and we're going to take a look at more of an analytical approach to understanding how a function looks like on a Cartesian plane. And lastly, and most importantly, because this is now where we are officially in the game with college trigonometry, we're going to use those rotation formulas we developed to rotate the axes and graph a conic when b itself is not equal to 0, which means we have an xy term. At the end of this, the only assignment you guys need to do for me today is if you have any questions, obviously that shared document right there on Google Classroom is where you can post any questions. I will answer them, or your peers can answer them to the best of your ability. And lastly, as always, I do want some video feedback. I am trying to make these more efficient as we go and save yourselves and myself, of course, time in the process. So, ladies and gentlemen, here we go. Once again, ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0 is that equation that for us defines any particular conic. So let us hypothetically say that a is equal to -1, b is equal to 0, c is 1, d is 0, e is 0, and f is 2. I'm going to take all those values and I'm going to plug them straight into this equation and see what I end up with. I've already taken the time to type this out, so hopefully the video itself will be quicker. So, bam, there it is. I do notice that there are two quadratic terms, so obviously the parabola is not in play at this point in time. You may be quick to call it a hyperbola because you see opposite signs. That definitely holds true. Whether or not it is a horizontal vertical parabola, or hyperbola, excuse me, is to be decided. We need to set it up in the general equation, which, of course, are things you can remember by looking at your textbook if you do not. So I think I'm going to subtract 2, most definitely, and I'm going to end up with this. And then obviously we always want to set this equal to 1. So I'm going to divide every group of factors by -2, which leads me straight to this right here. And voila, it is definitely a hyperbola. Based on the positive term, it gives us direction as to whether it is horizontal or it is vertical. So if I recall correctly, you guys have this great equation called b squared equals c squared minus a squared, and you recognize where a and b are relative to these two denominators, and c is the value you're looking for. That then allowed you to determine, first of all, the h and k. H and k are, of course, coming from the numerator. So it looks like this hyperbola is centered at 0, 0. My vertices relate to one of these particular values. And as you can see, since these are both squared, it would be the square root of that. And I'm moving 2 different directions. So that's why I move plus or minus at all times. Next value, of course, would be the foci. The foci comes from this equation right here of me plugging in a squared and b squared. Then I have the endpoints of the conjugate axis, if Mr. Kern would have used that term for you guys, and that comes back to the denominators themselves. And lastly, if you remember, there are 2 asymptotes that there are equations for, and if you do it correctly, you should recognize that the asymptotes in this case are plus or minus x. So what we have is the identity function working both directions. So from that point, you guys then took all this data information and you graphed it on a parabola itself. And I took the point already to give you a graphing calculator just to show you where everything would have lined up with. You can fast forward this if you feel comfortable about graphing. There is there we go. There is one vertex. There's the other vertex. There is the focus. There is the other focus. This is all just graphing review. This is the endpoints from the centers right there. So the endpoints of the conjugate axis would be approximately right about there-ish. Go very fast for you guys. The other one right about there-ish. Depending on who your teacher with, they may have taught you this creates a, try this again, there we go. This creates a box. I remember that's how I was taught in high school. I didn't really know why that was what it was, but it was a box. And the box extends through the endpoints of those conjugate axis. And the endpoints, struggling a little here with a smartboard presentation. There we go. Go through the vertices too. I should probably just copy this from my component. It didn't work out well at all. So let's undo that and do it again. And the asymptotes themselves were supposed to be the diagonals. I always thought this was a terrible method of teaching a student, especially when we could calculate the asymptotes themselves. So you guys maybe saw this sort of box, hopefully not. What you really saw is this right here, and the asymptotes developed. So that is how we graphed a conic in some sort of teaching levels. So let's go back to onto a different situation. Let's talk more about college algebra style. So let's take this equation and let's take a look at all this information and let's just plug it in. And that was pretty simple. My only problem, of course, is I cannot put this into the required form for a conic. In fact, I don't even know what conic this is, quite honestly. It's because of the existence of the XY term. But college algebra, I can still manipulate. And I remind you guys one more time, algebra is a process that allows you to take off in certain directions, to evaluate what you have and what you can deduce from what you have. So I think what I'm going to do is simply solve for y, which I was told to do thousands and thousands of times. So I'm going to add 1. I'm going to divide by x. And I get right to that equation right there, which I do recognize actually as a very much worked on equation in college algebra and actually in algebra 2. What do I know? I know that I can never divide by 0. So my domain cannot include 0. And since my domain cannot include 0, that implies that there is a vertical asymptote is equal to 0. At the same time, since there is a constant 1 in the numerator, there's no way I'm ever going to get 0 in a division problem, because it must be 0 divided by a non-zero number, which means that my range will also never be 0, which implies there's a horizontal asymptote with y is equal to 0. So this is how we used to do things in college algebra. And all I've determined is I have my function, and I have a vertical asymptote, and I have a horizontal asymptote. So what did I do? Well, I always grabbed what I referred as critical points. So I chose x to be 1 and maybe x to be -1, and I just calculated their corresponding y values. And that gave me 2 points to work on. Now let's use a little college algebra in analysis. What happens when the x values are heading towards 0, but they're heading from, let's say, the right side? This is notation in calculus that often conveys that information. As x heads towards 0, but from the positive side, what exactly is going on with the y values? Well, the numerator is positive, the denominator is always positive, so we know the y values are positive. And what I end up with is the constant being divided by an increasingly smaller number, which makes the quotient get very, very large. So what does it mean? It means that y is going to head off up. This is known as positive infinity. It's the idea that y is heading upward continuously as x heads closer and closer to 0 from the positive side. So all that's telling me is some sort of direction on the basis of these domain values. Well, what happens when x heads towards 0, but I'm from the left side? Well, in this point in time, of course, these numbers are always going to be negative, and a positive divided by a negative is negative. But the absolute value of these values are getting very, very small, which makes the quotient, of course, behave in a certain way. And what it really tells me is that the y values are going to head way down. So as I get closer, I'm just shooting downward at that point in time. What about when x heads off way out to the right, or what I'm going to call positive infinity? As these numbers are positive and they get increasingly larger, what happens to the quotient? Well, we know the quotient itself will be positive. And of course, the number is going to get smaller and smaller and smaller. 1/2, 1/3, 1/5, 1/billionth. So what we say is that y is going to be approaching 0, but from above. And lastly, the one we have not checked, what happens when those domain values head way off to the left? Well, same reasoning, I think you guys can figure out. It looks like the y values are going to be approaching 0, but from below. So what does that look like? Well, college algebra, you meet graph and a point, and meet graph and a point. Those are the two critical points. It's me recognizing, hey, there's an asymptote here. That's from the domain values. There's an asymptote here. That is from the range values. And this idea, which I smart work kicked off, you're going to understand much more in calculus, is the idea of something called a limit, which allows me to reason out what's going on with the graph. So if I just take my pen, there's my pen, let's have it be a blue color. What happens is x values get really, really big. We head off here. As x values get really, really small, they head off there. The same reasoning, head off there. And so what is this? This is definitely a hyperbola. And I took the time to find a graphing program for you that shows it a lot better than my example. There it is. That is a hyperbola. Notice, however, that hyperbola does not go upward or downward, or it does not open horizontally at all. Something has happened to the hyperbola. What exactly has happened? Well, that is what is referred to as rotation of axes. But notice I did not have to do any trigonometry whatsoever to figure it out. That is because this particular equation I can manipulate. So what happens if that is not the possibility, which is the very last part of our video today? Here we go. There's our beautiful equation. Let us say that we came across this situation right here, which leads to this. And I told you that we're going to use trigonometry and that your rotation angle will be 45 degrees. Well, there's the equation. I have an xy term, which in this case, b itself is not equal to 0. This looks vaguely familiar. Yes, we just did this exactly with college algebra, but I just want to show you to see how we can do it with college trigonometry. So what do I need? I need my developed rotation formulas. There is the one we did to find the relationship between x and x prime relative to the angle of rotation theta. And since I'm just going to do some math now, I'm going to plug 45 degrees in here. I definitely have memorized every value of my unit circle. Hopefully I'll never have to look at the chart. You'll never forget these for the rest of your life. I recognized 45 degrees is one of those angles I can always find exact trigonometric values of, and it is √2/2. So there we go. I'm just doing substitution. Now notice that both of these group of factors and those group of factors do have a √2/2. Some people like to leave it like this. I prefer to maybe factor out that √2/2 and clean up my equation to some extent. So apparently, x is equal to root 2 over 2 times the quantity of x prime minus y prime. Interesting. So what about the y coordinate? Well, there is the rotation formula for y, which relates it to the x prime, y prime axis and the angle of rotation of 45 degrees. I'm doing the same thing. I'm going to plug in my known value of theta. Notice it has been given to me. If it wasn't given to me, I would be stuck with nowhere to go. I'm going to evaluate the trigonometric values. And then once again, I'm going to clean it up a little by factoring out the root 2 over 2. You do not have to do the step. I would encourage you to do the step. I think you're going to find it's always going to be easier for you. So this dinky equation of xy is equal to 1. Let us now, since we've calculated x in terms of the prime axes and y in terms of the prime axes, let's do some substitution on this. So we're going to take that xy is equal to 1. I'm going to substitute in what I now know x to be and what y to be. Look at that right there. It looks hideous at the moment, but there's nothing that bothers us. We'll just think about this. And what I see is a number times a number times a number times a number equals a number. Since commutative property says it doesn't matter what order I multiply numbers, I'm just going to take the root 2 over 2 and multiply it by the root 2 over 2, which of course would give me 1/2, and use distributive property right here. Notice I never said FOIL. You will never say FOIL. That is not what it is. It's simply called the distributive property. FOIL is something you teach little children to memorize. So once again, FOIL equals profanity in this class. It is called the distributive property. And there we go. I did recognize these are conjugates, so the middle term does eliminate itself as a result. And now I have this right here. Well, that looks pretty close to a equation we were looking at earlier in slide 6. There it is. Just doesn't look the exact same. So maybe what I'll do is just make it look the same by taking that 1/2 and representing it in a different fashion. So ladies and gentlemen, what I notice is that this equation looks exactly like that equation, except this one is in the language of xy axis. This one is in the language of the x prime y prime axis. But the relationship of a squared and b squared and c squared, how to find the center, how to find the vertices, the foci, the endpoints of the conjugate axis, that mathematics still holds at all aspects. So let me grab a graph, because this is what it used to look like. There is all those values, but, and this is the most important thing to remember, they are not on the xy axis. They are on the x prime y prime axis, which is something that has been rotated xy axis 40 degrees. And the way I'm going to help you guys out, look, I made these little notes for you. The asymptotes themselves are the y prime, x prime, because everything is in terms of x prime and y prime. So you're asking me, Mr. What does this mean? Why am I looking at this graph? You're not looking at this graph. You are looking at a hypothetical graph that we rotated, there we go, 45 degrees. Rotation of axes. Notice that this graph looks the exact same as this graph because they should look the exact same. They are, as you can see, the exact same equation. Pause. Let it sink in. You hear that applause, thunderous. And so the fundamental question you should be asking yourself, why would you ever go through the process of rotation of axis in such a problem? The answer is you never would. Ladies and gentlemen, mathematics at the level you're at, there's many different ways to solve a problem. Find a way that is most efficient, but recognize that one way is not the best way in all situations. When would we ever use rotation of axes? That, of course, will be the next lesson. Have a great day. Make sure you check Google Classroom for a quick little assignment for video feedback and answer any questions you may have.